I always thought of sine and cosine as living in the world of triangles,
Yeah,
right? Like
yeah.
that was their natural habitat, and we were just visiting.
Right.
But then I learned that mathematicians have a completely different way of defining these functions, and it kind of blew my mind.
Yeah, it's pretty amazing. What's really fascinating about this other approach is that it goes way beyond triangles.
It's okay.
It starts by building everything up from a really surprising starting point, the number pi.
Hold on. Are you saying we're going to define pi first and then use that to figure out sine and cosine?
We are.
That seems backwards.
It seems counterintuitive, but trust me, it leads to some really elegant and beautiful results.
All right. I'm intrigued, but I'm not sure I'm following. So how does this lecture define pi?
Well, it defines pi as the area of a unit circle.
A unit circle, just for those of us who maybe need a little refresher.
Sure.
What is that again?
A unit circle is simply a circle with a radius of 1.
Okay.
Now, this is just one way to define pi, of course. But what's really cool is where we go from there.
All right, so we've got our pi defined as this area.
Yeah.
What's the next piece of the puzzle?
So imagine, like, a
Yeah.
function, right?
Fine.
And it calculates a specific area within that unit circle.
Okay.
So think of it like this. As we move along that horizontal line, like right through the center of the circle, our function is kind of measuring this changing area that's related to the circle's curve above it.
Okay, so I'm picturing the unit circle in my head.
Yeah.
So as we move further along that line, does the area get bigger, smaller? And that's what our function is capturing.
Exactly. You got it. And for now, let's just focus on this idea, like visually, right?
Okay.
Without getting bogged down in a specific formula, because it can get, it can get a little hairy.
Sure.
But the important thing is that this function, what it's doing is it's connecting lengths on the unit circle, which we can think of as being tied to angles to areas within the circle.
Okay, so we're linking lengths to these changing areas. I mean, you can see how that might start to feel a little bit like trigonometry, maybe. But where do sine and cosine actually come in? Like, how do we get from areas to these functions?
So this function, it has some very special properties, okay?
Right.
It behaves very predictably, meaning like as the input changes, the output changes in a very consistent way. And this is really crucial. It's what we call a one-to-one function.
One-to-one, and just to like refresh my memory.
Yeah.
What does that mean again?
Of course. It simply means that for every unique input that we feed into the function, we get a unique output. So no two inputs will ever give us the same output.
Right.
And this is going to be really important for the concept of inverse functions.
Inverse functions.
Exactly.
I vaguely remember those from like high school math class.
All right.
But how do they fit into all of this? How do we get to like sine and cosine from inverse functions?
Okay, so remember how we were talking about that function that relates like the lengths on the unit circle to those areas?
Okay.
All right, so the inverse of that function, and this is like a real aha moment, is actually what we call cosine.
Whoa, hold on. Are you serious? The inverse of that area function gives us cosine.
It does. It really does.
That's wild.
It's kind of amazing. It's a very elegant concept. So let's break it down a little bit, okay? An inverse function basically reverses the roles of the original function.
Okay, so it's like hitting the rewind button. So if our first function says, okay, this length on the circle, this goes with this area, the inverse is saying, okay, given this area, here's the length that matches it.
That's a really good way to think about it.
Okay.
Yeah. So if we have an angle, let's call it t, right?
Yeah.
And we want to find the cosine of t, we can use this inverse function, this magical inverse function. And basically we're asking what length on the unit circle, right, would give us this specific area that's related to this angle t. And that length is cosine of t.
Whoa, so we've just connected areas, lengths on the unit circle, and angles all through this like inverse function magic.
Yeah.
That's pretty cool.
Yeah, it's very cool.
So it's like we found this like secret backdoor into understanding what cosine really is.
Exactly. And once we have cosine defined in this way, sine becomes surprisingly straightforward.
Okay.
Because remember that every single point on that unit circle, it's got two coordinates, right?
Like a map.
Exactly.
You need both an x and a y coordinate to find out where you are.
Precisely. And on the unit circle, the x-coordinate of a point that goes with an angle t is represented by, you guessed it, cosine of t.
Okay.
And the y-coordinate, that's our sine function, sine of t.
Okay, so once we've got cosine figured out,
Yeah.
we automatically know sine as well for that angle.
You got it.
It's like two sides of the same coin.
And this connection, it goes even deeper, right? Think about the Pythagorean theorem.
Oh, right. A squared plus b squared equals c squared?
Exactly.
That's the one that tells us about the relationship between the sides of a right triangle.
And it applies beautifully to our unit circle because the radius of the unit circle is like the hypotenuse of any right triangle that we can draw inside of it.
Right, okay.
So just remember how any point on the unit circle, we can think of it as cosine of t, sine of t, right? Representing the x and y coordinates. If we apply the Pythagorean theorem to a right triangle inside the unit circle, with our point on the circle as one of the corners, we get cosine squared t plus sine squared t equals 1.
So that famous trigonometric identity, it's not just some, like, random formula that they make us memorize in school.
Right.
It comes directly from how we've defined sine and cosine using this whole area idea.
Exactly. And it doesn't stop there. A lot of other properties of sine and cosine that might seem like separate, like facts, they actually flow very naturally from these definitions.
Okay, like what? Give me an example.
Okay, so like derivatives, for instance. Now, we don't have to get into like the nitty-gritty details of calculus right now, but just know that a derivative tells us about the rate of change of a function.
Okay.
And it turns out that the derivative of cosine of it is negative sine of t, and the derivative of sine of t is cosine of t.
They're all connected. It's like this secret web.
They are all connected.
It's so cool.
That's very cool.
So from this, like one simple idea of defining pi as an area, we've uncovered this whole web of connections between these different concepts, areas, angles, lengths, even calculus. It's amazing. I'm seeing sine and cosine in a whole new light.
And the beauty of this is that it actually allows us to calculate like concrete values for cosine and sine,
Okay.
even for angles that are beyond the typical angles that we see in right triangles.
Okay, can we try an example? Because I want to see this in action.
Absolutely.
I'm a very visual person.
Okay, so let's picture our unit circle again.
Okay, got it.
And imagine starting at that far right edge of the circle.
Okay.
That corresponds to an angle of 0.
0. Okay, I see it, and I'm guessing that point on the circle is somehow related to cosine.
You guessed it. That point's x-coordinate, which is 1 in this case, is actually the same as cosine of 0.
Wow, okay. So we're using, like, our knowledge of the unit circle, these areas, and that special inverse function that we talked about, to be able to say what cosine is for these different angles.
Yes. And it gets even better because we can actually visualize the graphs of sine and cosine based on our initial area function.
Okay.
Since cosine is the inverse of that function, its graph is essentially a reflection of the original function's graph across like an imaginary line.
So we can, like, see the relationship between those two functions visually. That's so much more intuitive than the way I learned it.
Exactly.
That's really cool.
It's pretty neat.
But so this all works really well for angles that we can actually, like, see on the unit circle, like 0 degrees, 90 degrees.
Right.
But what happens when we go beyond that? What about, like, angles bigger than 360 degrees?
That's a fantastic question.
They're even negative angles.
Yeah.
Where do those fit in with this
Yeah.
whole area-based idea?
That brings us to like the heart of why this whole approach is so powerful. You see, it's not just about those initial angles. It's about setting up this like foundation that we can then extend to encompass all angles, no matter how big or how small.
So even though we've been focusing on this, like, limited part of the unit circle so far,
Yeah.
those ideas can actually help us figure out sine and cosine for any angle we can think of.
Yes.
That's really cool.
And the key to unlocking that is understanding this like fundamental property of the unit circle, its cyclical nature.
Cyclical nature. Okay, I need you to elaborate on that a little bit.
Okay, so imagine like a Ferris wheel.
Ooh, I like this.
Right. So you go around the Ferris wheel, you hit the same points again and again and again, right?
Yeah.
The unit circle's kind of like that.
So even though we're picturing a circle, it's almost like we're traveling along a spiral, right?
Right.
We hit those same points as we go round and round.
Exactly. So every time we go a full rotation around that circle, which, is 2 pi radians, we're basically back to where we started.
Ah, okay. So an angle of 360 degrees is the same as 0. 720 is the same as 0.
Yeah.
It's all about that repeating pattern, right?
Exactly.
Right.
And that pattern, that right there, is what lets us extend these definitions of sine and cosine beyond that 0 to 360 degree range, right?
Mhm.
We just have to figure out where a given angle falls on that unit circle. Like how many times we've essentially like wrapped around,
This is incredible. So even though we started with this idea of, like, pi as an area, and we've been looking at this kind of limited slice of the unit circle, we can use these ideas to, like, find the sine or cosine of any angle,
Yes.
any angle we can think of.
Any angle. And it all stems from this very elegant approach of building up from these basic principles. Like, we've gone way deeper here. We've seen how areas, angles, lengths, even calculus are all kind of intertwined in this, this really beautiful, dance of mathematics.
It's really elegant. I don't know about you, but I'm feeling simultaneously very, very smart, but also like I've just dipped my toe into this vast ocean of knowledge, and I want to know more.
And that's the best feeling, right? Like, it makes you want to go out and explore more and just keep asking those what if questions.
Totally. So for our listeners who are now hopefully, equally hooked on this fascinating world of trig functions,
Right.
we're going to leave you with a little challenge.
Okay.
So you've seen how we can define sine and cosine for those angles between 0 and 360 degrees using this area approach. But how could you extend these definitions to cover all angles? I mean, we're talking positive, negative. What about angles larger than 360 degrees? Think about that cyclical nature we talked about and see if you can connect the dots.
Yeah, it's a puzzle worth pondering. Who knows what mathematical wonders you might unlock?
And hey, maybe in a future deep dive, we'll come back, revisit this concept, and explore those connections even further. But for now, keep those mathematical minds buzzing. And remember, the most fascinating journeys, they often start with a single and sometimes surprising step.